那我刚刚讲那个趋停的那一段有 broadcast 出去吗？
因为那时候还没按直播。
那时候还没直播。
对
OK。
那时候。
Okay, so I have to repeat some of the information again because I just realized that what I said was not broadcasted. So we found some of the students they copy the code from others. So if you found that you get 0 for exercise 2, that is because we believe you copy the code from others. But if you are innocent, you can let us know and we will figure out what's going on later. And the TAs will announce an extra exercise as a makeup exercise. So if you get 0 for exercise 2, you can do the extra exercise. But the score will be 30% off. Okay, is that clear? And meanwhile, we will announce exercise 3 today. And for this exercise, you need to implement the logistic regression, and particularly you need to implement gradient descent, which means you need to update the theta such that the cross entropy loss becomes smaller and smaller. Okay, so that's what we discussed last week. Okay, so that accounts for 60% of your exercise 3. And you also need to implement the plot ROC curve function, okay, which accounts for 30% of your exercise 3. And then write a report, okay? So the due date will be November 22nd, which I think should be 3 weeks from today, okay? And so because next week you will need to present your midterm progress. So I assume that you probably cannot do much about the exercise 3 this week. Okay, so I start counting 2 weeks from next week. Okay, so which means you have the due date will be 3 weeks later. Okay, so here's something you should be included into your report for exercise 3. Okay, so I'll report some of the evaluation metrics. Okay, now let's ask some review quizzes. First, what is mean square error? So this should be straightforward to you now. So mean square error is used for a regression task, and it is defined as, let me open the pen. It is defined as yi subject yi hat square summation divided by n. Okay, this is mean squared error. What is R-squared score? So R-squared score is also used for regression. Okay, and it's always smaller than 1. Smaller or equal to 1. And if your regressor is a perfect regressor, which means your prediction and the target are always identical, then your R-squared score is 1. If your model, if the performance of your model is essentially equivalent to the naive mean regressor, then your R-squared score is 0. Next, what are the advantage and the disadvantage of gradient descent and stochastic gradient descent? Okay, so for gradient descent, essentially you need to go through all the training data instance once, then you can update the thetas. For SGD, you just look at one instance and then you update the theta. Okay, so for gradient descent, the cost of each step is very high, but the direction of each step is probably more accurate. But for SGD, the cost of each step is very low. However, it may or may not direct to the best direction. Although the expected direction is correct, but that's expected direction, but not necessarily the true direction. Okay, what is gradient descent and what is gradient ascent? Okay, so they are similar in the sense that I stopped talking because I need to close to the laptop so that my voice can be broadcasted. So I was closing the door in the classroom, and so I left the laptop for a couple of seconds. That's why I stopped talking. Well, anyhow, so gradient ascent and gradient descent are both methodologies to either maximize or minimize your objective function iteratively. Okay, so for gradient ascent, we update the thetas to be toward the gradient direction. For gradient descent, we update the thetas to the inverse direction of the gradients. Okay, and we show we show figures to explain why gradient ascent and gradient descent can do the trick. Okay, next, why do we usually maximize the log likelihood function instead of the likelihood function? Okay. Because, yeah, anything wrong? Okay, so, okay, so let's see. So that means we had some issues here. Okay, let's continue. But I don't think I need to repeat. I think the voice was broadcasted. It's just that the slide doesn't change to this slide, right? Yes. Okay. So it doesn't really matter because we were just asking some questions. So why do we usually maximize the log likelihood function instead of the likelihood function? So first, the thetas to maximize the likelihood function is the same as the thetas to maximize the log likelihood function. Okay, first, so we could do either one of them. And we usually use log likelihood function because when we take the log, the multiplication becomes summation. And last time when we introduced a log likelihood function, the probabilities are always between 0 and 1, which means that if we have a lot of IID samples, the probability for each of them is between 0 and 1. Then we multiply them together. Very soon, we may get underflowed values. So we use the log likelihood function because then we turn the multiplication of many small numbers become the summation of many small numbers. And adding many small numbers do not really cause underflow, but multiply many small numbers will underflow. Okay, so that's probably a major reason to use log likelihood function instead of likelihood function. Oh, and probably the other reason is that when we take the derivative, using the log likelihood function will make the result a little bit simpler. Oops, what's going on? Let's see what's going on. Okay. Next, what is logistic regression? Okay, so although this methodology has the name regression in it, but this method is used for binary classification. Okay, we encode the two classes as 0 or 1, and we try to fit an S-shaped function, and hopefully that S-shaped function goes through most of the observed data points. And so in linear regression, we try to find the thetas to minimize the residual sum of square error. But in logistic regression, we define the distance between observation and prediction based on cross-entropy loss, okay, which is the negative of the log likelihood function, if you remember. Okay, so we can either use gradient ascent to maximize the log likelihood function, or we could use the gradient descent to minimize the cross-entropy loss. They both give you the same theta. And by the way, this is your exercise, okay? And next, what is the cross-entropy loss for logistic regression? Okay, so we just discussed it. It's just the negative of the log likelihood function. Next, what is the RLC curve and what are its advantages and disadvantages? Okay, so we said that once you return a ranked list of your predictions, then by setting the threshold at different points, you would have different accuracy, different precision, different recalls, different F1 scores, those kind of things. So how to evaluate whether method A is better than method B or not? So essentially you have, based on different thresholds, you may get different results. An RLC curve is essentially look through all the possible thresholds and compute an overall score. Okay, remember it's essentially the relationship between true positive rate and false positive rate based on different thresholds, and then we connect all the points together, and we will form a curve. So that's, and we said that if everything is perfect, if your classifier is a perfect classifier, which means it puts all the positive classes in the top and all the negative classes in the bottom, then in that case, the area under RLC curve would be exactly 1, which is a perfect case. On the other hand, if all the positive classes are put in the bottom of your result, then you have essentially a inverse indicator. Then in that case, your area under RLC curve is 0. And if you just randomly pick positive or negative, the expected area under RLC curve will be 0.5. Okay, so that's probably the advantage of RLC curve, because it considers all possible thresholds, and we have the value, we have something to compare. But the disadvantage is that we need more computation. Right? We need to look through all the possible thresholds. If you use precision, recall, F1 score, those kind of things, you just pick a threshold, usually 0.5, and then you report the result. You just need one threshold and you get the result. But for RLC curve, you need to compute all different thresholds. So computationally, it's more costly. Explain precision and recall. Okay, so precision is whenever your model predicted as positive, what's the percentage that it's indeed positive? That's precision. And recall is out of all the truly positive instances, what's the percentage of them are predicted as positive by your model? Let's recall. Okay. Next, why F1 score takes the harmonic mean of precision and recall instead of the arithmetic mean. And I think we gave a numerical explanation last week, because harmonic mean essentially in the numerator you need to multiply precision and recall. So if either one of them is very small, the entire F1 score will be small as well. Okay, so we don't want we don't want one of them to be very small and the other is very large. That usually means something goes wrong. We want both precision and recall to be not too small. And only in that case, your F1 score will not be too small. Next, explain sensitivity and specificity. Okay. So sensitivity is, out of all the positive cases, how many of them are predicted as positive by your model? Recall is, out of all the negative cases, how many of them are predicted as negative by your model? So that's sensitivity and specificity. So sensitivity is equivalent to recall. And if you are from the biomedical domain, or if you are doing some kind of bioinformatics, these people usually like to the sensitivity and specificity. If you talk to a doctor or someone work in the medical school, they prefer to use sensitivity and the specificity. But if you are in computer science domain, I exclude the bioinformatics for a second. Most computer science domain, we prefer to use the terms like precision, recall, F1 score, these kind of things. Okay. Okay, so this is just yet a reminder for your midterm presentation. So, oh, by the way, so I received an email from a international student who said that he or she just arrived in Taiwan and he or she are still in the hotel. He or she cannot be here physically next week. So he or she asked me like what he or she can do. So if you have teammates who can physically attend the class, I think you will be okay. All right? Okay, so let's continue our discussion. Okay, let's see. I think we stopped here last week. Let me open the OBS. Okay, so I think we stopped here last time. So I was asking, can we apply logistic regression on multi-class classifier? So if we use decision tree classifier or k-nearest neighbors classifier, then apparently we can apply those techniques on multi-class classification problem directly. But for logistic regression, which is a binary classifier, can we apply this technique to a multi-class classification problem? That's what I'm asking right now. Okay, so it seems that we cannot use it directly. So there are certain algorithms that can only deal with binary classification. But even in that case, we can sort of remodel the task a little bit such that the binary classifiers can be applied on a multi-class classification problem, and here's how. So we will introduce two widely used methodologies, one called one versus rest, or one versus all, and the other is called one versus one. And so I think perhaps today or after the midterm presentation, we will introduce a very famous methodology called SVM, support vector machine, which is also a binary classifier. And for like methods like SVM or logistic regression, we can use this technique to deal with multi-class classification. Okay, so first, one versus rest or one versus all. Using this as an example, assuming we have three labels, red, blue, and green. So it's a tri-class classification problem. And so for one rest, essentially we build three classifiers. If we have k classes, then we build k classifiers. And each one of so we have F1 up to Fk, k classifiers. And the first one is used to predict class 1 or not. The second one is class 2 or not, up to the last one, class k or not. Okay, so we build k classifiers, and each of them can use all the training instances for training. And once we build k classifiers, then at the prediction phase, we have a new instance xi. We just put this xi to all the k classifiers, and then see which one gives us the largest result. Then we just pick that one. Okay, so this is called one versus rest or one versus all, because we use one class versus the others. For each classifier, we essentially is a binary classifier. It's either class I or the other class. Next strategy is called one versus one. So again, if we are dealing with a canary classification, we have k classes. Then we build CK choose 2 classifiers. So the first classifier, let's use 1, 2 to denote. This classifier is used to distinguish class 1 and class 2. And F13 is used to distinguish class 1 and class 3, and so on, up to Fk-1 and K, which is used to distinguish Ck-1 and Ck. Okay, so in total we have K choose 2 classifiers. And each of them use part of the training instances for training. Okay. So that's for prediction. And that's for training. And for the prediction, you have a new instance xi. And again, you just put this xi to each of these classifiers. And then, for example, the first classifier may say, okay, this belongs to class 1. The second one may say it belongs to class 1, and so on. And the third one may say it belongs to class, class 4 or something. And so on. And then eventually you just count which class received the most votes. And you just predict this xi as that class. So if we compare these two, one versus rest and one versus one, which one is better? Or perhaps let's think about which one is faster in terms of training time. So the first thing is that it seems that if we use the one versus one methodology, we need to build CK choose 2, which is roughly k squared, order k squared, this much classifiers. But if we use the one versus rest, we only need to build k classifiers. So from this point of view, it seems that using one versus rest is more efficient. However, there's another thing you need to consider. For each classifier alone in the one versus rest approach, assuming we have n training instances in total, n training instances in total, then for each classifier in the one versus rest methodology, their training instance is n. Number of training instances is n, because each instance is either class I or not class I. Okay, so for each classifier, you need to use n training instances to build a classifier. But for one versus one, like this F12, you only use the instances that belongs to either class 1 or class 2. You can ignore all the instances that belongs to class 3, class 4, class 5, or they can be ignored. So, for each classifier alone, it seems that 1 versus 1 might be faster because the training instances is, the number of training instances is smaller. Okay, so which one is faster? That really depends. It depends on the number k, how many classes you have, and the number n, how many training instances you have. When you have different binary classifiers, when you have different number of classes, when you have different number of training instances, sometimes 1 versus 1 might be faster, sometimes 1 versus rest might be faster. It really depends. Okay. So next, I will introduce some metrics for multi-class classification. So last time we spent quite some time to introduce the metrics for binary classifiers, binary classifications. And now we will discuss some multi-class classification, which might be relevant to binary classifier, but they are still different. Okay, the first one, very straightforward, accuracy. Okay, so this is just, now we are dealing with multinary classification. So each yi, if that's for example a trinary classification, then each yi can only be 1 or 2 or 3. Your yi hat eventually can also only be 1 or 2 or 3. Okay, so we just count how many times you're predicting yi hat equivalent to the yi, sum them together and divide it by n. That's accuracy. Very straightforward. Next, we introduce cross-entropy loss for multi-class classification. So we introduced cross-entropy loss for binary classifier. If you remember in the lossy regression, right? We try to minimize the cross-entropy loss to find the thetas. But for multi-class classification, the cross-entropy is sort of like an extension of the binary cross-entropy. So the definition is like this. Summing all the, so here the k is the label. So you just compute p of yi equals k multiplied by log p of yi hat equals to k. And then this summation is essentially summing all the training instances or test instances, depending on you are computing training loss or testing loss. Okay, so I'll give you an example. If we have 3 classes and the probability that a certain yi hat equals to class k, so here k can only be 1 or 2 or 3. Okay, so yi equals to first class, the probability is 1 over 4. The probability that yi is the second class, is also 1 over 4. And this one is 1 over 2. And if, in fact, this instance belongs to second class, then by cross-entropy loss, this will be 0 log 1 divided by 4, 1 multiplied by log 1 divided by 4, plus 0 multiplied by log 1 divided by 4. So this will give us 2, okay, because these logs are base 2. Okay? So think about in the binary class, okay, if your yi can only be either 0 or 1. And let's say your yi hat is, for example, let's say a certain yi is indeed 1. And your yi hat is, for example, 0.8. Then in the cross-entropy loss we introduced last time, it's defined as negative summation yi log yi hat. Remember? Plus 1 minus yi log 1 minus yi hat. And because now we are dealing with binary classification, so that means when yi is 1, one subset yi is 0. And if your yi hat is 0.8, that means one subset yi hat is 0.2. So essentially that's the same as the definition here. Okay? Also, for binary classification, for logistic regression, of course, you don't need to use the you don't need to use the cross entropy loss for the multi-class. But when you are when we will a couple of weeks later, we will introduce multi-layer perceptron, or you could call it deep learning or neural network. We will introduce those techniques, and for those kind of models, you can use this cross entropy loss for multi-class classification directly. So which means you build a network. Let me give you a very high-level overview about like how to train a deep neural network. Again, in this deep neural network, there will be a lot of different parameters, but you don't know the good parameters. Okay, so you use something very, very similar to gradient descent to update the thetas, such that your predicted yi hat and the real yi to be closer and closer. And how to define the distance between a yi and yi hat if we are dealing with a multi-class classification, then we can use this cross entropy loss. Okay. So at that moment, we might see this equation again. Okay, next, confusion matrix. Okay, so we saw confusion matrix for binary classification last week. And now we are going to look at the multi-class classification. Okay, so here I give a 3-class classification. Either the fruit is an apple or an orange or a mango. So these are the true classes. These are the predicted classes. So that means 7 apples are predicted as apples. 1 apple is predicted as orange, and 3 apples are predicted as mango, and so on. So this is the confusion matrix. So once we have this confusion matrix, how to define precision? So in binary classification, precision is defined as whenever the model claims something as positive, what's the percentage that they are indeed positive? That's for binary classification. But here we have 3 classes, or even more than 3 classes. Then how to define positive and negative classes? Right? So that's the problem. So depends on how we compute the precision. So let's first introduce something called macro precision, and we will introduce some other kinds of precisions later. So for macro precision, we treat one class as positive and the others as negative and compute the precision. And then we just repeat this process for different classes. Okay, so I'll give you an example. If we treat apple as positive, the others as negative, then based on this confusion matrix, we predict 7 plus 8 plus 9. We predict these 24 classes, 24 instances as positive, because now we regard apple as positive. Out of them, only 7 of them are indeed positive. Okay, so the precision is this much. Likewise, here we regard orange as the positive class. So out of the 6 classes that are, out of the 6 instances that are predicted as orange, only 2 of them are indeed orange. Okay, so precision is 0.33 here. For mango, here, out of the 6 instances that are predicted as mango, only one of them is indeed mango. Okay, so this is the precision. So the first definition of macro precision is I just average these 3 as my final result. This is the first definition of macro precision. But unfortunately, we have there's another way to compute macro precision, and you will see both kind of definitions in the paper. So let me introduce another kind of macro precision. Oh, I'm sorry. Where's that? Where is that? Oh, sorry, I made a mistake. So macro precision only have one definition. It's macro F1 score that has two different definitions. Okay, sorry. Okay, so recall. What is macro recall? So again, we just treat each class as positive and compute a recall and repeat the process for different classes and average them. Okay, so again, here if we treat Apple as positive class, then what's the definition of recall? Recall is that out of the truly positive classes, what's the percentage of them are predicted as positive by my model? So here we have, in fact, 7 plus 1 plus 3, 11 fruits that are indeed apple. And out of them, 7 are predicted as apple. Okay, so recall is this much. Orange. I have A plus 2 oranges. And out of them, 2 of them are really predicted as orange. Okay, so this is recall. Likewise, I have 13 mangoes. And this one is predicted as mango. The others are predicted as not mango. So this is the recall. Okay, so here, macro recall is simply the average of these 3. Did I introduce micro precision? Oh, sorry, so I somehow missed this slide. Okay, so we have something called macro precision, and there's another thing called micro precision, which somehow I didn't know why I skipped this slide earlier. But anyhow, what is micro precision? So remember that precision is the original definition of precision in the binary classification is TP divided by TP plus FP. That's the original definition in binary classification. The reason is that TP plus FP is the total number of positives predicted by my model. Okay, so this is the original definition. And here, I just regard each class as positive and compute the TP and FP in all the situations, and then summing all the TPs and FPs based on this formula. So if I treat Apple as positive, then the true positive is 7. False positive is this 8 plus 9. They are predicted as apple, but they are not. Okay, so false positive is 17. If I treat orange as positive, then this is number of true positive, and 1 plus 3 is the number of false positives. Likewise, for mango, this 1 is true positive. This 3 plus 2 are negative. False positive. Okay, so micro precision is summing all the TPs in the numerator, summing all the TP and FPs in the denominator. That's micro precision. Right, so if we compare the macro precision with micro precision, it's which one should you use? Okay, so it depends on what you want. If you believe that, if the number of instances in each class are roughly the same, then use micro precision or macro precision will give you roughly the same result. However, if your class is highly imbalanced, for example, you have 10 apples, but you have 100 oranges and 100 mangoes, then if we compute the macro precision, it's sort of like each apple will be 10 times more important than orange and then mango. But if we use the micro precision, then every instance will be roughly the same important. So it's choosing macro or micro precision, that really depends on what you want. If you believe that each class should be roughly the same important for your final task, then you probably should use macro precision. However, if you believe that every instance should be roughly the same important, you should use micro precision. And if the number of instances in each class is roughly the same, then whichever you use, there's no much difference. Okay, so for recall, we talk about macro recall already, right? We just compute a recall for each class and then average them. That's macro recall. For micro recall, that's very similar, because for our original definition of recall in the binary classification, that's TP divided by TP plus Fn. And we just extend the definition here. Okay, so if we treat apple as positive, then what's the recall here? I'm sorry, what's the true positive here? True positive is 7. Okay, and false negative is what? False negative is it's predicted as not apple, but you are wrong. That's false negative. So this I'm sorry, where is it? Oh yeah, so these 4 instances, they are indeed apple, but they are predicted as not apple. So they are wrong. Okay, so we have 1 plus 3, which is 4 here. Okay, if we treat orange as the positive class, okay, then this 2 is true positive. And this A plus 2 are predicted as not orange, but they are indeed orange. Okay, so this A plus 2 is the false negative of orange. If we treat mango as the positive class, then this is true positive. And these 12 instances, in fact, they are mango, but you predict them as not mango. Okay, so they are false negatives. Okay, so the micro precision is you summing all the true positives in the numerator and summing all the true positive and false negatives in the denominator, and you get the result. So likewise, if you compare macro recall and micro recall, which one should you use? Again, it depends on your what you want. If you believe that each class should be roughly the same important, you should use macro recall. If you believe that the importance of a class should be proportional to the number of instances in that class, then you should probably use micro recall. Oh, by the way, if you need to do the makeup exercise, then this is part of your makeup exercise. You need to implement this kind of macro precision, macro recall, micro precision, micro recall, and these kind of things. You need to implement this by yourself. Okay, now we talk about F1 score, and we will talk about 4 different kinds of F1 scores. Macro F1, micro F1, weighted F1, and simple F1. And this F1, macro F1 score, in fact, it has 2 different variations. So let's look at what they are. Again, let's use the same example. So macro F1, it has 2 different definitions. Definition number 1 is, we know how to compute the macro precision and macro recall earlier. So our F1 score is simply the harmonic mean of these 2 numbers. That's definition number 1. Definition number 2 is, for each class, we compute the precision and recall. And then, of course, we can compute the F1 score for that particular class. And then we average these three. That's another definition of macro F1. Unfortunately, if you look at a paper, usually they won't tell you which one they use. And I don't think many people realize that there are two different kinds of macro F1 score. And if you use sklearn, if you use its methodology directly, it uses the definition number 2 here. But occasionally, you will see people use definition number 1. Okay, so it's 2:50. Let's have a 10 minutes break. We will come back at 3. Okay, let's continue. Okay, so there's two different definitions of macro F1 score. Now let's discuss micro F1. Okay, so we know how to compute micro precision and micro recall, right? So micro F1 can just be 2 times harmonic mean of micro precision and micro recall. And for a multi-class classification problem, micro recall and macro recall, they happen to be the same number. So I think the reason is you just plug in the number. Oops. Where is it? Okay. So you just plug in the numbers and you will see why. Let me open the pen here. And there's another thing called weighted F1 score. So weighted F1 score is we compute the F1 score for each class just like before. And then we compute a weighted sum of these F1 scores. And what's the weight? The weight is just how many, the percentage of the apples, the percentage of the oranges, and the percentage of the, I was wrong. Sorry. Let me erase the marker here. Erase pen. Okay. It's the weight of the number of apples, number of oranges, and number of mangoes. Okay, so in the denominator we divide it by the total number of fruits. Okay, so essentially we just compute a weighted sum of the F1 scores based on the ratio of each class. Okay, next we talk about multi-label classification. Okay, so multi-label classification and multi-class classification, they are different. Multi-class classification is you pick exactly one class out of k possible classes. That's multi-class classification. But multi-label classification is you could select 0 or 1 or 2 or 3 or even k classes out of all the choices. Okay, so in Chinese, it's sort of like 复选题 and 多选. What's that? So it's like a 选择题 or 多选题. Okay, for multi-class classification, you can only select 1 out of k classes. For multi-label classification, you could select 0 or 1 or 2 up to k classes. So here's an example, assuming that the possible labels includes A or B or C. And here we have 4 instances. And this is the truth. This is the prediction. And now we want to evaluate how good the prediction is. And how to do that? We will introduce something called the simple F1 score. Okay, so we use this as an example to illustrate what is the simplest F1 score. So essentially, we need to compute the precision recall and F1 score for every sample and then average them. That's why it is called simplest F1 score. For the first sample, the true label is B, and the predictor is predicted as B and C. So what's the precision? Then let's think about what's the original definition of precision. Precision is that when the predictor predicts something, what's the percentage that is correct? Okay, so you just consider like the predictor predicted B and C as the positive. A is the negative, it's not there. Okay, so it's predicted B and C as positive. And the truth is only B is positive. Okay, so precision is 1 divided by 2. What's the recall? Okay, recall is out of the truly positive classes, or here, the truly positive labels, what's the percentage of them are predicted as positive by my model? So here, we have only one positive label, which is predicted as positive by our predictor. Okay, so the recall is 1. So the F1 score is, again, the harmonic mean of precision and recall. So after all the computations, we just get the F1 score, the precision, recall, and F1 score for just the first instance. And so next, we need to do the same thing for the second instance. Right? So here, the truth is B and C, and we predicted as B and C. So both precision and recall will be 1. And of course, F1 score will be 1 as well. Next, the truth is A and C, but we predict B. Okay, so in this case, precision and recall are both 0. And of course, the F1 score is 0 as well. Next, the truth is C, but we predict it as an empty. Okay, so it depends. So can we select no answer or not? That depends on the task. Okay, so there's no universal definition here. But let's assume that you can select empty. If that's the case, then here, both precision and recall are 0. So here you will have a 0 divided by 0 issue, but we define this as 0. Okay, so for this sample, precision and recall are both 0, so F1 score is 0. For the final one, the truth is empty, but we predict A as positive. So here, again, both precision and recall are 0, so F1 score is 0. Okay. Then we have 5 instances, and we have 5 precision recall and F1 scores. And what's the simplest F1 score? It's just the average of all the F1 scores for all the samples. Okay, so we have the simplest precision, simplest recall, and simplest F1 score for this multi-label classification task. Now let's think about an interesting case. What if we add one more sample, and the truth is empty, and we predict it as empty? This should be a correct guess, right? This should be correct. Conceptually, this should be correct. But if we use our previous definition, the precision, recall, and F1 score for this 6th instance, they will all be 0 based on our previous definition. And then the simple average of precision, recall, and F1 score would of course become smaller. So this is obvious. This should be incorrect. And in fact, if we use scikit-learn's where is it? Samples average here. I use the same sample I just illustrated. You will see that for the true label of the last instance is 0, 0, 0. For the predicted, it's 0, 0, 0. And I compute the macro, weighted, and samples precision recall and F1 score. And then this is the table. And you will see that the sample average here are the same as the problematic results here. So there's probably an issue. I think I talked about this issue, I don't remember, last year or 2 years ago, and I encouraged the students to submit a patch to scikit-learn. But I don't think anyone did that. If you are interested, of course you could do that. Right? This is obvious an issue. So you should be able to report a bug or a patch to scikit-learn. Does that make sense or not? Or if you think I'm wrong, of course we could discuss. But I think this instance should be regarded as a correct guess, which means precision and recall and F1 score for this instance should be 1. Okay. So if you really want to sort of correct this problem, how can you do that? So here's a possible suggestion. Okay, you could try to do that. So I just regard the empty case. I just assign a new symbol to this empty class. So here I use this, what's this? Is it, how to pronounce it? Is it Kasai or what? Who knows how to pronounce this Greek letter? Is it Kasai or something else? Anyway, let me call it X for now. I don't remember how to call this Greek letter. Let's call it X for now. Okay, so you replace all the empty symbols as X. And then you can do the same computation as before, I think. Okay? Because the only case that X would appear is these empty cases. Okay, then you can compute the precision recall and F1 score. And you will see that for samples 4 and samples 5, their precision recall and F1 score are the same as before. But for the 6th instance, its precision and recall and F1 score will all be 1. And then, oh, by the way, I don't see any, so as I told you, I don't see, this is, I think this should be an issue for scikit-learn. And you are welcome to submit a patch to, I think you are encouraged to do that. Okay, let's summarize what we have learned. So for binary classification, we encode yi as 0, 1, or -1, +1. And if we use logistic regression, then the output should be between 0 and 1. So you are sort of encoding the yi's to be either 0 or 1. So logistic regression is trying to find the parameters to fit the logistic function, which is an S-shaped function. And we, just like in linear regression, we apply the LK norm on the parameters to prevent overfitting. So we could use either gradient ascent or gradient descent to find the thetas. We use gradient ascent if we try to maximize the log likelihood function, which is equivalent to minimize the negative of the log likelihood function, or the cross-entropy loss. Okay, so in that case, that's gradient. We use gradient descent to find the theta. We talk about some different evaluation metrics. We talk about accuracy, precision, recall, sensitivity, specificity, true positive rate, false positive rate, based on the confusion matrix. And we also talk about ROC curve and the area on the ROC curve. And today we also talk about the evaluation matrix for multi-class classification. Okay, so as before I close this topic, let's do some quiz. First, what is accuracy? Okay, this is very straightforward. The number of successful predictions divided by the total number of predictions. That's accuracy. What's precision? What's recall? We talked about this for several times today. Precision is when your model predicted as positive, what's the percentage of them are indeed positive? That's precision. Recall is out of the truly positive cases, what's the percentage of them are predicted as positive by your model? What's the advantage? Oh, so we talked about this question in our earlier quiz when we started the class, so I skipped this question. How to apply logistic regression on a multi-class classification task? So we could use either one versus rest or one versus one technique to apply a binary classifier to a multi-class classification problem. Explain the difference between multi-class classification and multi-label classification. So we just talked about it, right? Multi-class classification, you can select exactly one class at a time. For multi-label classification, you could select 0 or 1 or 2 up to k classes at a time. Okay, next, if you are given this confusion matrix, how to compute the macro F1, micro F1, weighted F1 based on these numbers. So let's just explain a little bit, but the details I will leave you to do it by yourself. So essentially, you need, let's just use one example. So to compute if we regard A as the positive case, then the TP will be these two, right? And the FP will be 1 divided by 0, right? They are predicted as positive, but they are wrong. Okay, so it's 1 plus 0. Okay, and what's the let's see. So based on these numbers, you could compute the precision, right? Based on these numbers, you could compute precision. It's essentially just TP divided by TP plus FP. How about recall? For recall, it's we need to, out of all the truly out of all the instances that truly belong to A, how many of them are predicted as A? Okay, so recall would be TP divided by TP plus what's this? This should be Fn. Okay, so TP is, so we also need Fn. Fn is this 2 plus 0, so it's 2 plus 0. Okay, so you can repeat this process for all the different classes. Then you can compute the macro F1, micro F1, or even weighted F1. Okay, so let me close the slides here, and we will move on to the new topic, which is a very relevant topic, which I want to discuss precision and recall curve and the ROC curve a little bit further. So we spent some time talk about ROC curve, which is the relationship between true positive rate and false positive rate based on different thresholds. And we also talk about precision and recall curve a little bit. Essentially, again, it's just compute all the different precisions and all the different recalls based on different thresholds and connect all the points together. So when to use which? That's what I'm asking right now. When to use which? Okay, so most of the contents I'm going to present later are from these two papers. Okay, so I don't think I need to repeat this again. We talked about this several times. But let's look at the precision and recall curve example here, because last week we talked about ROC curve as an example, but here I want to use precision and recall curve as an example. So if we set the threshold really, really high, then the precision is 0 divided by 0, but previously in ROC curve we defined this as 0 directly. But here let's just put a question mark here. We will decide whether 0 divided by 0 will be whichever. We will decide the value later. But recall is apparently 0 divided by 6, because out of the 6 truly positive cases, none of them are predicted as positive. Okay, so if we set the threshold here, the precision is 1, because this is predicted as 1, and it's indeed 1. Okay, so precision is 1. Recall is 1 divided by 6, because we have 6 positive classes, and only one of them is predicted as positive. Okay, if we set a threshold here, then out of the first 3 will be predicted as positive, but only 2 of them are indeed positive. So precision is 2 divided by 3. Recall is 2 out of 6, because out of the 6 positives, 2 are predicted as positive. Okay, so we just repeat all the process, and then you would have this curve here. Okay, I use the precision in the y-axis and the recall in the x-axis, and I just connect all the points. But I leave this as a question mark here. I will decide the value here later. So you have two choices, two obvious choices. One is you probably could always connect to 0 and 0. Or you could always connect to 0 and 1. Okay, so we will decide the value later. But let's look at another. So if we connect with this 1 and 0, then this is area. You could compute the area under this PR curve. Okay, so in this case, the total area will be this much. Let's look at case number 2. If the first instance is in fact 0, then by selecting all the if we put here, then TP is 0, FP is 0, TN is true negative is 1, 2, 3, 4. And the false negative is 1, 2, 3, 4, 5, 6. Is it? 4. 1, 2, 3, 4, or 5. Sorry, it's 5. Okay, because true positive is out of all the positive cases, how many of them are predicted as positive? I'm sorry. True positive is that's what I was talking about. It's not true positive. True positive should be. It's positive and it's predicted as positive. How many of them are like this case? Okay, so true positive is 0. False positive is I predicted as positive, but I'm wrong. Okay, so it's also 0. True negative is I predicted as negative and I'm right. So all of them are predicted as negative, and among them 1, 2, 3, 4. 4 of them are indeed negative. Okay, so true negative is 4. False negative is I predicted as negative, but I'm wrong. So which means all the ones here Oh, sorry, so that's 6, right? This should be 6. 1, 2, 3, 4, 5, 6. This should be 6. Okay, I predicted as negative, but I'm wrong. Okay, so that should be 6. Okay, so you could compute the precision and recall based on this. So precision should be 0 divided by 0. Recall should be 0 divided by 6. But again, how to define this? Okay, so let's look at this here. No matter you start from 0, 0 or 0, 1, in this case, they don't give you much difference. When we compute the area on the curve, they don't give us any difference. Okay, so for PR curve, we will just define this as 1, because in anyhow, we just define it as 1. Okay, so we'll start from this point and then draw all the other things. Okay, now let's discuss the property of PR curve. So the area under PR curve is apparently between 0 and 1. But here the AUC is different from the AUC I discussed last time. Last time I discussed area under ROC curve. Here I discussed area under PR curve. Okay, so although I use AUC, but they are different things. But here, area under PR curve is also between 0 and 1. However, in ROC curve, the worst case area under curve is 0. The best case area under curve is 1. But for PR curve, there are some unreachable areas, which means even in the worst case, the area under PR curve will not be 0. And I will show you why this is the case and how to interpret the result. So in fact, the area of the unreachable region is influenced by this thing, the number of positives divided by number of negatives. So let's look at some example. If I give you 10 instances and 3 of them are indeed positive and 7 of them are negative, then let's think about what's the best classifier, what's the worst classifier, and what's just random guess. So let's think about for a perfect classifier. What's a perfect classifier? The perfect classifier will put all the 3 positives at the top and all the zeros at the end. That's a perfect classifier. A worst classifier will be put all the zeros in the front and the 3 ones at the end. That's a worst classifier. And for a random guess classifier, it's sort of like all the ones will roughly equally distributed among the 10 instances. So let's look at the perfect classifier, okay? So a perfect classifier, which means these 3 instances are in fact 1, and all the others are in fact 0. That's the truth. And then, so the precision and recall, you can compute the precision and recall here. And then if you really connect all the precision and recall together, you will get area on the curve, which is exactly 1. So that's a perfect classifier, which is the same as in the ROC curve. Now let's think about a random classifier. Again, out of 10 instances, 3 of them are positive. Then what is precision at K? At K means that if I have only 3 instances, then how many of them are positive? If I just predict the top 3 as positive, then how many of them are indeed positive? Okay, so that's precision at K. So if I random guess, then essentially, what's my expected accuracy? It's 3 over 10. What's my expected precision? Again, it's 3 over 10, right? Because I'm just random guess. Okay? So the expected precision at k is always 3 over 10 for different case. How about recall? The expected recall is proportional to k, right? Because the definition of recall is out of all the positive classes, how many of them are indeed positive, right? So if I predict the first one as positive, because I'm just randomly, or I'm sort of random guess, and then break a result, and I claim the first one as positive, then in that case, the expected recall would be 1 divided by 10. If I move the threshold a little bit lower, I claim the top 2 as positive, then the recall is 2 divided by 10, and so on, right? I'm talking about the expected value. So that means if I plot the precision and recall, the precision is always 3 divided by 10, and recall will go from 0 to 1. This is the expected curve, the expected trend. Okay, so I have a plot here. So this is, so apparently in this case, the area on the curve is not 0.5, it's 0.3. How about the worst classifier? The worst classifier means that I put all the ones are here, all the zeros are in the front. And you plot, you compute all the precision and recalls. And you, essentially, this is the curve. So the area under PR curve is not 0, even for the worst classifier. And you can never reach this area. So this is the unreachable area. If you are given 3 positives and 7 negatives, you will never get an area under PR curve that is smaller than this number. So what we have learned so far, if we have m positives, if we have m positive and m negatives, then, and if we use a PR curve to evaluate a classifier, for a perfect classifier, our precision at k is n divided by k. So let me explain what is p at k for a moment. Here I say p at k as I cut threshold here. This is k. I claim for p at 2 here, I claim the first 2 as positive, all the others as negative. And what's the precision in that situation? So for a perfect classifier, the precision is at k is n divided by k. Okay. So why is that? So sorry, this is wrong. So this should be because this might become larger than 1 if k is very small. So I should correct this. For a perfect classifier, p at k should be mean of, and let's see, p at k should be 1 if k is smaller or equal to n, and it's n divided by k otherwise. Okay, does that make sense? Because let's look at an example. If I have 3 positives and 7 negatives, and for a perfect classifier, then I would have 3 ones and 7 zeros. Right? And if I cut the threshold here, precision is 1. Here, precision is also 1. Here, precision is also 1. Only if my k is larger than the number of positives, my precision becomes n divided by k. Okay, so this is wrong. This should be correct. Here, this should be correct. Okay, how about recall at k? If k is larger than n, then of course recall is always 1, because you predict all the you identify all the positive cases. Okay, so recall is 1. But if k is smaller than n, then recall is k divided by n. Okay, again, if we go back to this example, when k is 1, which means threshold is here, then your recall is 1 divided by 3. If the threshold is here, the recall is 2 divided by 3. If threshold is here, recall is 3 divided by 3. And from now on, your recall is always 1. Okay? So perhaps I could continue to write the precision at k as mean of 1 or n divided by k. It's precision. And recall is very similar, but it's the mean of k divided by n or 1. Okay, so that's a perfect classifier. How about a random classifier? So precision at k is, the expected value of precision at k is this much. This is the expected value. Okay. How about recall? So recall essentially goes from 0 to 1, and it's a straight line. Okay, so its expected value should be k divided by n plus n. And the area on the curve, because that will become a triangle. Okay, so the area under PR curve is this much. I'm sorry, not a triangle. It's not a triangle, a rectangle. It's a rectangle. So for a random classifier, your recall and precision is like this. Here is 1, and here is n divided by n plus n. So the area on the curve is the area of this rectangle. Okay. For a worst classifier, precision is 0 if your k is less than m, because the first m instances are indeed negative, but they are predicted as positive. Okay, so for the first k instances, the precision is always 0. And then for the others, the precision is this much. For recall, again, for the first m instances, the recall is always 0, and then it started to go from 0 to 1. So this is the area on the curve is a little bit harder to compute. You need more steps to compute the area on the curve. But essentially, this is the area under curve, and this is the what we call the unreachable area, because you just cannot. If you have n positive and m negatives, it's impossible that your area is smaller than this shaded part. So let's think about some cases when the positive instance is the minority class, which means the number of positive is smaller than the number of negatives. If this is the case, then what's the precision at k required at k and the AUC for different n's and m's? Okay, so we have 4 positive and 6 negative, and if you compute for a worst classifier, the area under PR curve is this much. If we have 1 positive and 9 negatives, then the area under PR curve is this much, and it's smaller than the first case. If we even make the positive class even more, the ratio becomes even smaller, then the area on the PR curve is even smaller. So that means that if the ratio of the positive instances is very small, then the unreachable area will become smaller as well. Now let's think about when the positive case is the majority. Okay? If we have 6 positive and 4 negatives, this is the area under PR curve. It looks much larger than the 0.0 something before. If we increase the ratio of the positive instance for a worst classifier, the AUC is 0.73. So if I just report this area under PR curve, it seems okay from first look, but it's the worst classifier you could get. It's impossible to get a PR curve whose area under curve is even smaller than 0.7 something when you have 9 positive and 1 negative. Okay, if we make the ratio of the positive instance even larger, the area under curve is 0.8 something. Okay, so if someone tells you that my classifier performs really, really well, the area under PR curve is 0.9. Does that really mean he or she has a very good model? It depends. We don't know. We need to know the number of positives and the number of negatives. Then we can know whether, let's say, area under PR curve is a good number or not. Okay, so if our positive is, the number of positive is 19, number of negatives 1, this is the unreachable area. The unreachable area is really, really large, which means even the worst classifier has a really large area under PR curve. Okay, so I list some numbers here. The number of positive versus number of negatives. For a perfect classifier, the area on the PR curve is always 1. For a random classifier, the area under PR curve equals the number of positive divided by the total number of instances. For the worst classifier, there, I cannot list the formula that easily, but essentially, when the number of positive instances becomes larger, the unreachable area becomes larger, which means that even the worst classifier may have a large area on the curve. And if we fix the positive ratio, for example, here, the positive ratio are both 0.1. And then in this case, if n plus m is larger, then the unreachable area will be a little bit larger. So this is a little bit larger than here, even though the positive ratio are the same here. Likewise, here the positive ratio are the same, but this one is a little bit larger than this one. So let's look at this figure for the relationship between PR curve and the F1 score. So here, this part is the unreachable area for a certain for a certain case. And here we have the contour plot of the F1 curve, which means for all the data points on this line, their F1 scores are the same. So here I plot the relationship between precision and recall. Okay? So every data point on this line, their F1 score are all 0.6. So you will see that if we compare point A and point B and point C, they all have the same F1 score. However, you can never reach the point A because it's in the unreachable area. It's impossible, based on this data set, it's impossible to get something whose recall is close to 1 and whose precision is roughly 0.3 because it's in the unreachable area. Even for the worst classifier, the area on the curve is, the PR curve is above this point A. For point B, although it has the same F1 score as point A, it can be reached. But you will see that it's very close to this unreachable area. So from the perspective of its distance to the unreachable area, it looks like data point B might not be that good because it's very close to the unreachable area, which is the worst classifier. If we see point C, its F1 score is the same as the point B, which is the same as the F1 score of point A. But this is far away from this unreachable area. So perhaps here is a better choice. So anyhow, so here the positive ratio is 0.33, which means 1/3 of them are positives, 2/3 of them are negatives. In this case, we have the unreachable area here, and the F1 score for all these 3 data points, they are 0.45. But point C is probably, if you need to cut the threshold somewhere, perhaps you should cut at the place where you get the point C. So let's compare ROC curve and PR curve. For a perfect classifier, the area on the curve are both 1. For a random classifier, area under ROC curve is 0.5. Area under PR curve depends on the positive ratio. For a worst classifier, area under ROC curve is always 0. Area under PR curve is 1 subtract the unreachable area. So the advantage of ROC curve is that it's easier to interpret. Once you give the number, you know how good or how bad the classifier is. And what are the advantage and disadvantage of PR curve? If you really care about successfully predicting the positive cases, if the positive case is what matters, and if the number of positive classes, positive instances is much smaller than the number of negative instances, then perhaps you could use PR curve. Okay, so when to use which? First, you can always report both areas, right? You can always report both. But if you really need to select one and you don't know which one to pick, then I think my first priority would be RLC curve because it's easier to interpret. However, if in your working scenario, if successfully identifying the positive case is more important, and if the positive is the minority class, then perhaps area under PR curve is more appropriate. Okay, so here I give you an example. If the data contains 2% positive, then area under PRC curve will focus on successfully predicting these 2%. Okay, that's essentially the key idea of PR curve. So if your model really handles this 2% really well, then area under PR curve will be large. Otherwise, it will be very small, but it won't be zero, right? Because there's always some unreachable area as long as you have positive instance. So it's 3:51. Let's have a 10 minutes break to 4:01.
师，我想问一下，就是报告的时候是一个。
Okay, let's continue. Alright, I think in literature, most of the time you will see people report area under ROC curve for most of the time. It's less frequently that people report area under PR curve, and that's probably because if you can just give one number, it's hard to tell like how good or how bad your classifier is. However, it's not saying that you cannot use PR curve or area under PR curve. It's just that you need to select when to use which carefully. And to do that, to be able to distinguish when to use which, you need to know what we just discussed. So essentially, if your number of if the positive ratio is very large, it's larger than 0.5, then in this case, you report area under PR curve was sort of a little bit sort of like trying to manipulate the numbers such that your result looks good. Right? Because no matter what, even a random classifier will give you 0.5. And it's very so if your positive ratio is even larger than 0.5, then it is very likely that even the worst classifier will give you 0.7 or something. However, if the positive ratio is very low, and if in your scenario you really care about successfully predicting the positive cases, then perhaps you could use area under PR curve. But you have, I think, if you want to use area under PR curve, you should also report the number of positive instances and number of negative instances in your training data and your test data so that we can have a fairer judgment about your model. Okay, quiz. If you're given 10% positive and 90% negative, okay, so that's the distribution of the data you are going to evaluate. And if you have two methodologies, you have two models, model 1 and model 2. Model 1's area under ROC curve is 0.6. Model 2's area under PR curve is 0.3. Which one is better? So in this case, we really don't know. Okay, because M1's area under ROC curve is 0.6, means that M1 is better than random guess. And for model number 2, it's if that's random guess, its area under PR curve should be roughly 0.1. So again, model 2 is better than random guess. But which one is better, we really don't know. If given another model, model 3, is it possible that model 3's area under ROC curve is 0? It is possible. When model 3 is an inverse indicator, although unlikely, but it's possible. Is it possible that model 3's area on the PR curve is 0? It's impossible. Okay? As long as we have some positive instances, its area on the PR curve cannot be 0. There's always some unreachable area. Okay, we move on to next topic. Okay. Now we are going to talk about support vector machine, or SVM. So first, let's talk about linear support vector classifier. We are given a data instance xi. It has d different features. And support vector classifier is also a binary classifier. Okay, so we have only two classes. But instead of encoding the two classes as 1 and 0, we encode them as 1 and -1. And we want to find a hyperplane to separate these data points. And here I assume that all the data points, they are linearly separable, which means that you can find a hyperplane in the high dimensional space that can perfectly separate the positive and negative instances. So here I have some, I use 2D example. We have some circle classes and triangle classes. And they are indeed nearly separable. And you can see that there are, in fact, infinite number of choices, infinite number of classifiers, linear classifiers, that can perfectly separate these two classes. So which one should we use? Okay, so for example, we could pick this one or this one. These dashed lines means classifier. I use this dashed line here to mean classifier. So both of these two classifiers, they can perfectly separate these two classes. And which one should we use? So we want to choose the one that has a large margin. So what do I mean by margin? Margin is the distance between the classifier to the nearest instance. This distance is called the margin. Okay? This distance here is called the margin. So we want to find a classifier that can perfectly separate the positive and instances. Meanwhile, we want to maximize the margin. Why do we want to maximize the margin? Because if we use this the classifier at the left-hand side here, this circle here, if it just moves a little bit, it will be regarded as negative if we use this classifier. If we use the classifier at the right-hand side, this classifier has to move larger distance to be misclassified. Okay, so that means if we have a classifier that has a larger margin, that's probably more robust, because even if the instances change their axis for a little bit, their predictions are still the same. Okay, so anyhow, if we define this hyperplane as W transpose X plus B equals to 0, then we want that for all the positive instances, we want that W transpose Xi plus B to be larger or equal to 1. And W transpose X plus B to be less or equal to -1 for all the negative instances. So which means that this dashed line here, it's W transpose X plus B equals to 0. And this dashed line, if here is positive class, here is negative class, then this line here means W transpose X plus B equals 1. And this line here means W transpose X plus B equals to -1. And, okay. So if we can find such a W and such a B, then at the prediction phase, you are given a new X. You just compute W transpose X plus B and see whether that's positive or negative, and then the sign is positive or negative, and that's your prediction. Okay, so So how to compute the distance and how to compute how to find the W and B such that the margin is maximized. So if we are given two parallel hyperplanes, H1 and H2, whose formula is like this: W transpose X equals to B1 and W transpose X equals to B2. Then the distance between these two parallel hyperplanes is this much. I think you probably learned this or some variation, some simplified version of this in high school. How to compute the distance between two parallel lines. Okay, anyhow, this is the distance between these two lines. So if we want to maximize the margin between, let's say, these two lines, the distance between them is this much, right? 2 divided by the L2 norm of W. So in other words, if we want to maximize the margin, we want to maximize this thing, right? If we want to maximize the margin, let's go back to the, if we want to maximize the margin, that means we want to maximize the distance between this line and this line. Okay? So, in other words, we want to find W and B such that the distance between these two parallel hyperplanes are maximized. And this is equivalent to find the W and B such that the inverse of this margin distance is minimized. Okay? And it turns out that this is a standard quadratic programming problem. We want to minimize this objective function, this inverse of the margin distance, subject to our constraint here. Why do we have this constraint? Because here we assume that all the data points, they are linearly separable. And for the positive instances, we want that W transpose Xi plus B is larger or equal to 1. For all the negative instances, we want that W transpose Xi plus B is smaller or equal to negative 1. So that means if we multiply this sim by Yi, they are always larger or equal to 1. Okay, here for Yi equals to 1, we want W transpose Xi plus B to be larger or equal to 1. For Yi equals to negative 1, we want W transpose Xi plus B to be smaller or equal to negative 1. So because of this, so we have this constraint here. W transpose Xi plus B multiplied by Yi to be larger or equal to 1. Okay, so we are talking about training instances. Okay, of course, for test instances, there might be a different story. But for training instances, they have to follow this constraint. And we want to maximize the margin, which is equivalent to minimize the inverse of the margin. So before I tell you how to solve this, let's discuss something. What if the data points are non-linearly separable? So in this example, it's still linearly separable because I can, for example, find a line here. Okay, so that's still linearly separable. But if I have a positive instance here, then that's non-linearly separable. Right? But anyhow, so I said that I assume that all the data points are linearly separable. But what if it's non-linearly separable? Or in this case, although it's linearly separable, but perhaps we allow some errors, and if the margin can increase a lot, we probably allow some errors. Okay, so here, although this one is incorrectly predicted, but the margin becomes very large, right? The margin is this much. However, if we use this green line as the model, then although we perfectly separate the positive and negative instances in the training data, the margin is very small, which means if you change the value a little bit, the value of the x a little bit, you get a different prediction. Okay, so anyhow, we want to minimize the inverse of the margin. At the same time, we probably allow some errors. If making a little bit of mistake can really enlarge the margin a lot, we probably allow this kind of trade-off. Okay, so this part is sort of like prevent overfitting. Because if we have a large margin, it's sort of like we have a more robust model. Okay. And so, of course, if C becomes infinite, then essentially we allow no errors at all. If C is 0, then basically we ignore. If C is 0, that means we want the margin to be as large as possible. So essentially, we don't care about the training loss at all. Okay, and next, we want to step further. We want to introduce something called a slake variable. So the idea is that not all mistakes are equally bad. So in the previous slides here, I said I want to minimize the inverse of the margin. Meanwhile, I also want to minimize the number of mistakes, and each mistakes are equally important. But now, I want to minimize the inverse of the margin distance. Meanwhile, I also want to minimize this thing. And what is this thing? This is sort of like how bad your mistake is. Okay, every mistake might be weighted differently. So, previously I said that I assume that all the data points are linearly separable. So I have a constraint that is yi multiplied by w transpose xi plus b has to be larger or equal to 1 for all the instances, for all the training instances. But now, if they are non-linearly separable, I allow some mistakes. So the constraint becomes yi multiplied by w transpose xi plus b should be larger or equal to one subject. How to call this? Kasai or something? How to call this? Is it called? Is it called Kasai? And let me check real quickly because we will see this number again and again in this slide. Let me check how to pronounce it. Where I believe there's a Wikipedia page. Talking about all the Greek letters. It's called. Where is it? Oh yeah, it's called Kasai. Okay. Okay, so anyhow, for example, this, let me open the pen again. So this instance here is incorrectly predicted. It should be at the negative side, but it's at the positive side. So we want this one to be at least on this side of this this hyperplane. Okay, so this is the error of this instance. Likewise, this one should be here. So this one is wrong, and this the sort of like the penalty of this one is this much. Okay, so for different instances, we have different cosine. And for all these data points that are at the right side of the hyperplane, their cosines are exactly 0. Okay, so that means for the correctly predicted instances, there's no error. But for the incorrectly predicted instances, their error is proportional to their distance to the right side. So our subjective function becomes one subject cosine. Yi multiplied by this has to be larger or equal to one subject cosine. Okay, so this is called a soft margin classifier, which means that now we don't assume that all the data points can be linearly separated. Okay, even if they cannot be linearly separated, we can still apply the concept. We want to maximize the margin, and we allow some mistakes, and the mistakes are not equally weighted. So why soft margin? First, the data points may not be linearly separable. Second, even if the data points are linearly separable, perhaps if we allow some mistakes, we could increase the size of the margin a lot. And that's probably a reasonable trade-off. Okay, so essentially we have two objectives. First, minimize the training error, which means we want to prevent the error, or we want to increase the robustness. And second, we want to maximize the margin because that prevents overfitting. Okay, so this is our original formula. We want to minimize this inverse of margin subject to this constraint. And our new formula becomes, we add the Slake variables. We allow some mistakes. And we want to minimize the mistakes. And we also want to minimize the inverse of the margin. And this is the constraint. Okay, so the problem becomes how to find the W's such that this is minimized, and also subject to these constraints. How to find such W? Okay, and this C here is a hyperparameter. Okay, controls the overfitting or underfitting. And this cosines is called Slake variables. Okay, so before I continue, let's think about how to solve this. If I want to use, what's our strategies in linear regression and logistic regression? How to find the thetas such that the loss function is minimized? We use gradient descent, right? You did this in your exercise. So let's think about it. Can we use gradient descent directly here? So here the unknown is the W's. C is a hyperparameter. Cosine is also another hyperparameter. Well, it's not really a hyperparameter, but once you decided the W's, the cosines are decided. So and yi's, xi's and yi's, they are given. They are the training instances. So the only unknowns are W's and B's. So how to find the W and B such that our objective function is minimized, subject to some constraints? If we use gradient descent directly, which means we take the partial derivative of the objective function to W and to B's, and then update the W's and B's based on the directions of the gradients, what might happen? Can we do that or not? if we do that directly, we may end up having some w's and b's, although that might minimize the adjective function here, but it may or may not follow these constraints. Right? When we do the gradient descent, we don't have any sort of any limitations on the parameters. So it is possible that even if we minimize this, the result doesn't really follow these constraints. So it seems that we cannot use gradient descent directly. So what can we do? So it turns out that the above questions here is equivalent to the line here. So let's look at what this is. So here is the inverse of the margin size, okay? And this is the hyperparameter. So let's think about if a data instance is correctly classified, then that means its corresponding psi would be 0 if this instance is correctly classified. So that means one subject, so if this is correctly predicted, that means this term here, yi multiplied by w transpose xi plus b would be larger or equal to 1. So let me write it down. If a certain data instance xi, yi in the training instance that's correctly classified, correct, that means its corresponding psi I would be 0. And that also means yi multiplied by w transpose xi plus b would be larger or equal to 1. And that also means this part would be smaller or equal to 1. And max of these two things will be 0. Right? So that means if this data instance is correctly predicted, we don't have empirical loss. Otherwise, if a certain xj, yj is incorrectly predicted, then there will be some psi. Right? Psi will be larger than 0. And then in this case, we will have some error. And how much is the error? The error will be, let's go back. This distance here is the loss, right? So the loss will become this much. Why is that? Because based on this equation here, a certain psi j would be a certain psi j would be one subject yi w transpose xi plus b, which is this is j, which is exactly here. So if a certain psi j, this is j, if a certain psi j is positive, then this will be the loss. Okay, so anyhow, the above problem here is equivalent to the formula here. We want to find the w's and the b's such that this entire equation here is minimized. Then let's look at this question here. C is given, it's a hyperparameter. All the xi's and yi's, they are given, they are the training instances. And we want to find the w's and b's such that this is minimized. Then can we use gradient descent here? So if we want to use gradient descent, this is the objective function. We need to take the partial derivative of this objective function to w and b's. And now, do we have any constraints on w's or b's alone? No, right? Because we sort of incorporate the original constraints into this formula already. So we don't have constraints on w's and b's. As long as we can minimize this equation, that's fine. We don't have any constraints on w's and b's. So we can use gradient descent again, which means the initial w's and the initial b's, they are randomly assigned. And we update the values based on the negative direction of the gradients. So so we do the derivative of this objective function. We take a partial derivative to a certain w, wj. Remember that here the w is w1 up to wd. Okay, if our certain xi contains xi1 up to xid. Okay, so if we take the partial derivative of the objective function to a certain wj, then this part will give you only wj, right? Because this is essentially w1 squared plus w2 squared up to wd squared. So the partial derivative of this thing to a certain wj will give you only wj. How about this part? Okay, take the partial derivative of this to this, then that depends on whether this is larger or this is larger. Right. If 0 is larger, then partial derivative of 0 to a certain variable will give you 0. Okay, so it ends up having only wj if this is 0. So if this part is 0, that means this instance is correctly predicted. So that means yi multiplied by w transpose xi plus b is larger or equal to 1. If this one is larger, that means this instance xi yi is incorrectly predicted. Okay, so we take the partial derivative of this part to wj, that would end up giving us only this part. So if a certain instance is incorrectly predicted, then this is how we update the wj. So let's look at this updating formula a little bit. Then you will think that makes sense. Why is that? So our wj would be what? Our updating formula for the k plus 1 round is the value at the kth round subtract eta multiplied by this gradient here. Right? This is the gradient descent formula. And think about it. If a certain instance is successfully predicted, then it seems that let's look at it. Let me think about it a little bit. Let me think about it a little bit. Oh, sorry, forget about what I just said. Anyhow, so this is the result. So you should be able to use gradient descent to update the form. I was thinking about the other thing, but then I realized that I probably think about something wrong. So just skip what I wrote here. So anyhow, now you can solve the linear SVM based on gradient descent or stochastic gradient descent. Wait, okay. So this is the pseudocode of gradient descent and stochastic gradient descent. You compute the gradient based on these instances and update the W. Or you could you can compute the gradient based on single xi and update the w's. Now, before I continue to talk about something called kernel SVM, I need to detour a little bit to talk about some other things. Then we need to we have enough background knowledge to talk about kernel SVM. But let me introduce what's kernel SVM briefly. So in the setting here, we sort of trying to find a W whose dimensionality is the same as the feature size. Okay, so if we have D features, then we want to find a sort of like a hyperplane in the D-dimensional space. Although it may or may not be perfectly separate all the training instances because we allow some select variables. Okay, so but anyway, our model is a hyperplane in the D-dimensional space. That's the linear SVM. But what I'm going to introduce next is something called kernel SVM. So kernel SVM is sort of like the imagination is sort of like you project the data points from the original D-dimensional space into a higher dimensional space. For example, it could be D square dimensional space. And in that higher dimensional space, you try to find the hyperplane in that higher dimensional space such that the data points are separated. That's a sort of like a visual imagination of kernel SVM. And the problem is how to do the projection. Okay, you want to project the data from D-dimensional to even higher dimensional. How to do the projection? And even more, it's probably hard to imagine at this moment. Later on, I will show you that we can in fact project the data points into infinite dimension, such that in that infinite dimension, we can find a hyperplane to separate the data points. If you could project the data points into infinite dimension, then mathematically you could separate everything. So what I mean is that for any two data points, let's assume that when their features are the same, their labels will always be the same, if that's the case. If you have two data points whose features are the same, but their labels are different, then of course you will always make some errors in those cases. But let's assume that as long as your features are the same, your labels will always be the same. If that's the case, then by using the kernel SVM, theoretically, the training error can always be zero because you can always project data points into infinite dimension such that in that infinite dimension, you can find a hyperplane to perfectly separate all the data points, of course, in the training data. That's a sort of like a quick overview of what is kernel SVM, but the details are much more complex. It's hard to imagine how to project something to infinite dimension, right? Even if you can somehow project something to infinite dimension, then the size of W has to be the same as the size of the dimension. How can you store something that's infinite dimensional? That seems impossible for a computer, but there's some trick to do that. Okay, so let me detour first. Let me introduce something called Lagrange multiply and the KKT condition, and then we will come back to kernel SVM. And there are a lot of details, so you might get lost. So from now on, you have to be very, very focused, or at least we have some recordings, so you can check the recordings later. Okay, so let me detour to Lagrange multiply and KKT condition. And let me give you a toy example first. So if I want to maximize this 5x1, x2 subject to some equality constraints, okay, I want to maximize this thing. And my constraint is 2x1 plus x2 has to be 100. Okay, how to solve it? You might be able to solve this based on some simple techniques like this. You just put x2 equals to 100 subject to x1, right? Then your f of x1 and x2 becomes this. Then you take the partial derivative to x1, set it to 0, solve the equation, and you will find x1 should be 25. And in this case, x2 is 50. And then, that's the extreme value. Okay, that's one possibility. So this works if the constraint is not complicated. But if your constraint is very complicated, this might not be that easy. So that is where we need this technique called Lagrange multiplier. So in the previous example, if I give you another constraint, which is, I don't know, like let's say 4x1 plus 3x2 has to be something else. I give you some even more constraints. So the problem might become less easy. So Lagrange multiplier is like this. If you want to find the maximum or minimum of a certain f of x, subject to some equality constraint, which is gi of x equals to 0. So you have g1, g2, g3 up to gm, which means you have m different equality constraints. Okay? Then you can construct a Lagrangian, or called Lagrange function, like this. Your y lambda, this is something you constructed called Lagrangian. Okay. This Lagrangian is f of x plus lambda 1 g1 of x plus lambda 2 g2 of x up to lambda m gm of x. Okay, so the extra term is all these lambdas. These lambdas are called Lagrange multipliers. Okay, and so your Lagrangian becomes f of x plus summation lambda I gi of x, where gi of x are your equality constraints. And some textbook might write f of x subject this, and that doesn't really matter because well, this negative sign will be absorbed by this lambda, so that doesn't really matter. If you see a Lagrangian function written like this, that doesn't matter. And what you need to do next is you take the partial derivative of your Lagrangian to every xi and to every lambda I, set them to 0, solve the equation, and then test all the solution sets, see which one give you the maximum or minimum results, and that's your solution. So last 5 minutes, I'll give you a toy example. So this is our original toy example, right? I want to maximize this subject to this single equality constraint. Let's try to solve this based on Lagrange multiplier. So this is my Lagrangian. I'm sorry, this is my objective function. This is the equality constraint. I have to write the gi of something equals to 0. Okay, so this is the gi. 2xi plus 2x1 plus x2 subject 100 equals to 0. Okay, so this is the gi of x. So the Lagrangian becomes f of x plus lambda 1 g1 of x. This is the Lagrangian. Then I take the partial derivative of the Lagrangian to x1 and x2 and lambda 1. Set them to 0, trying to solve the equation. And then you will find that this is a solution set. Okay, and indeed, these 25 and 50, they are the same as what we solved earlier. Now let's talk about generalized Lagrange multiplier. So previously, we want to maximize or minimize something subject only to the equality constraints. But for generalized Lagrangian, it allows inequality constraints. So Lagrangian multiplier is generalized to the to include the inequality constraints under something called the KKT condition. These are just three mathematicians, right, under the KKT condition. Okay, so what's the generalized Lagrangian multiplier? Now we want to minimize f of x. It has to be minimized. Okay, if you want to maximize something, you just minimize the negative of that thing. That would be the same. Okay, so anyhow, you want to minimize f of x subject to some inequality constraints and some equality constraints. I have less 2 minutes, so let me quickly talk about how to do that, and we will see the example next time. So the Lagrangian will be f of x plus lambda igi of x plus mu j hj of x. That's your Lagrangian function. And then, let me skip these slides real quickly and go to where I want. You take the partial derivative, set it to 0, solve the equation. And then, for all the equation set, you have to check something. You have to check whether each solution set follows something called KKT condition or not. If it doesn't follow this, so we have some conditions here. The solution set has to follow this KKT condition. Then that could be the values to maximize or minimize your objective function following all the constraints. Okay, so if you have the two equation sets here, the next thing we need to do is check whether they follow the KKT condition or not. And in this example, all the lambdas has to be positive or 0. And because for this solution set, the lambda 2 is smaller than 0, so that cannot be our solution. So that leaves us only the solution here. Okay, so I'll stop here, and we'll talk more details about what's KKT conditions, and we'll go back to this example, I think perhaps next week or 2 weeks later.
我先停掉一下，好，先停掉。